In this video, we'll learn how to solve higher degree polynomial equations using synthetic division and the rational zeros theorem. Recall in the previous video that we were able to solve the polynomial equation in the last example because we had a clue about one of the zeros. In this video, we're going to remove that clue and learn how to start from scratch. This is where the rational zeros theorem comes in. So our goal is to solve a higher degree polynomial equation, which you can see represented in general over here. Remember, the highest exponent that we can find is what we call the degree of the polynomial. That also tells me how many solutions to expect. So a degree in polynomial equation should have at most n solutions. Now, other important anatomy that will come to play in our solution is our leading coefficient. That a sub n, or the coefficient of our highest powered term, is what we call the leading coefficient. Also important to our process will be this constant term, the term that does not have the variable. We call that a naught. So we're going to need to identify both the leading coefficient and the constant term. So here's how the rational zeros theorem works. If P over Q is a rational zero, so pause right there for a minute. Notice our solution is expressed as a fraction. Remember, a rational number is a number that can be written as a fraction. So this theorem is only going to help me to find rational zeros, but we have to be aware that irrational zeros or imaginary zeros also might exist. So we're going to find these easy ones first. We're going to narrow in on the rational zeros. So if P over Q is a rational zero of the polynomial equation, and P over Q is in lowest terms, then P, the numerator of our rational zero, is a factor of the constant term, a naught, and Q is a factor of the leading coefficient, a sub n. Okay, that's a lot of information to take in, but you're going to see it's easier in practice than it is to read the theorem. So let's take a look at example 7. Consider the following polynomial equations. List all the possible rational zeros. So first of all, observe, we are working with a degree 3 polynomial equation. So that tells us to expect at most 3 solutions. Now, for our rational zeros theorem, we're going to need to identify the leading coefficient and our constant term. So our constant term, we'll start there, which we generally call a naught, is equal to negative 20. And what we want to do is list all of the factors of this constant term, because remember, P, the numerator of our rational zero, is a factor of the constant term. So all of our P's are going to be the factors of negative 20. And we're going to consider both the positive and negative versions of those numbers. So the factors of 20 would be positive and negative 1, positive and negative 2, 4, 5, 10, and 20. 1, 2, 3, 4, 5, 6. So I've got 6 numbers in the list, but when I consider both the positive and negative, that's potentially 12 factors of negative 20. Next, we want to identify our leading coefficient, which we call a sub n, and in this case, it's 1. Now, the Q's are going to be all the factors of 1, so that's just going to include positive and negative 1. Now what we want to do is form every possible ratio of the form P over Q. That is, we want to put every possible P over every possible Q. Now this is the easiest case scenario, by the way, for the rational zeros theorem when you have that leading coefficient of 1. Because when I put every possible P over every possible Q, 1 over 1, 2 over 1, so on and so forth, we just end up with the P's again. So every possible rational zero, which can be formed as P over Q, would include positive and negative 1, 2, 4, 5, 10, and 20. So we call those the possible or the potential rational zeros. So if our polynomial equation has a rational solution, it is somewhere in that list. but not every number in the list is going to be a solution. Okay, let's practice that again on the next example. So in this case, we have a degree 5 polynomial equation, and we would expect at most 5 solutions. Now, important to the rational zeros theorem, we'll have our leading coefficient and our constant term. So my leading coefficient we call a sub n, and the constant term we call a naught. Now remember, the p's are the factors of our constant term. So we're going to list every possible factor of -3, including both the positive and negative versions of those factors. So for -3, the only factors will be plus or minus 1 and plus or minus 3. The q's are going to be the factors of our leading coefficient. Our leading coefficient in this case is 4. The factors of 4 include 1, 2, and 4. So this one's a little different than example A because we have more q's in this example. Next, what we want to do is form every possible ratio of the form P over Q. So I want to take every P and put it over every Q. So I'm going to do this in a systematic way so that I don't leave anything out. And remember, we always recognize both the positive and negative versions of these factors. So I'm going to take the first P, which is 1, and form a ratio with every possible Q. So we're going to have 1 over 1, which of course reduces to 1, 1 over 2, and 1 over 4. So that takes care of our first P. Then we're going to take our second P and put it over every possible Q. So that's going to give us 3 over 1, which is just 3, 3 over 2, and 3 over 4. Now, those aren't in numerical order, but in that list, we have every potential rational zero. Now, check out the note below. The rational zeros theorem only gives potential or possible rational zeros. It does not tell us whether these rational numbers are actual zeros. The rational zeros must be confirmed with synthetic division. So here's the way I like to think about the rational zeros theorem. If you've ever seen those movies where they take a list of possible suspects and they put them in a room behind a one-way mirror, and then you have someone on the other side of that mirror trying to identify the culprit in the crime. That's kind of what we have here. This is going to be our lineup, and we're going to interrogate each one of those suspects. We're going to interrogate with synthetic division to determine which one is the culprit, or in our case, which one is the solution. So here's the procedure for doing that. To solve a polynomial equation using the rational zeros theorem, do the following. Number 1, list all potential rational zeros of the polynomial equation. That is, form all of the possible combinations P over Q. Then I'm going to take each zero and test it with synthetic division. I'm looking for a remainder of 0. If I get a remainder of 0, I have found a solution. If the remainder is not 0, we can let that one go. That suspect is not going to be the culprit, right? And then number 3, continue dividing out all potential zeros until we have found every single one according to the degree of the polynomial, or until the depressed polynomial can be solved by factoring or quadratic formula. Okay, hopefully that procedure will become clear on example 8. Find all zeros of the following polynomial equations. So first of all, we want to know, what are we looking for? Notice this is a degree 3 polynomial. That's the highest exponent I can find. So we're going to expect at most 3 solutions. Now, to get started, we need some suspects. So we're going to figure out every possible rational zero. So our leading coefficient is 1. That's our a sub n. And our constant term is 10. That's our a naught. Remember, the p's contain every possible factor of that constant term, including plus, minus of each factor. So the factors of 10 include 1, 2, 5, and 10. And then our q's are going to be the factors of our leading coefficient. Well, this is the easy case because the only factors of our leading coefficient would be positive and negative 1. So then we're going to form every possible combination P over Q. And once again, if I take all of those P's and put them over the Q, each one of those numbers divided by 1 just generates the list of P's again. So every possible rational zero includes 1, 2, 5, and 10. So if our degree 3 polynomial has a rational zero, it's somewhere in this list. And we just have to figure out which of those suspects is the culprit in the crime. Which of those candidates is a solution to the equation? So I'm just going to pick the first P. Positive 1 is a potential rational zero. And we're going to confirm whether it is or isn't using synthetic division. So we're going to put the 0 in the box, and then we're going to identify the coefficients of our polynomial. There's no missing powers, so we can just pick up the coefficients, 1, -6, 3, and 10. Skip a line and bring down your number. And then remember, we multiply and add all the way across. And notice we have a remainder of 8. We are looking for a remainder of 0. Since our remainder is 8, then we can say 1 is not a 0. We'll let that suspect go free. That's not going to be one of our zeros. Well, let's try the next number in the list. How about -1? I'm using the same coefficients from the original polynomial, and we're going to inspect the remainder here. So multiply and add all the way across. This one works out a little differently. That's what we're looking for. We can see that our remainder is 0. Since the remainder is 0, then -1 is a 0 of the polynomial. So we have found one of the 3 answers for this polynomial equation. Now let's kind of keep track of the algebra. We started with the 3rd degree polynomial equation, which looks something like this. And we have now found one of the zeros. If -1 is a 0 or a solution of that polynomial, then it came from the factor x plus 1, right? The factor and the solution have opposite signs. Well, if that's one of the factors of the polynomial equation, well, what's the other factor? Remember, the other factor lives right here. So we started with degree 3. After one round of synthetic division, these numbers represent the coefficients of a degree 2 or a quadratic polynomial. So the other factor would be 1x squared minus 7x plus 10. So at this point, we have arrived at a quadratic trinomial. That's within our comfort zone to factor. So let's break that one down into 2 linear factors. We're going to have an x in the first 2 spots. Because this sign is positive, the signs in our binomial factors are going to be the same. And this one tells us that they're both going to be negative. So we're looking for 2 factors of 10 with a sum of 7. And that would be 5 and 2. So we have factored our original polynomial, although not by our traditional methods. We had to start out with that synthetic division. And once I have the factors, those code our zeros. So out of our first factor, if we set that equal to 0 and solve for x, we get x equals -1. The 0 from our second factor is 5, and also from our third factor is 2. Notice 5 and 2 are also in our list of potential rational zeros. So we can conclusively answer the question, what are the zeros of this polynomial? I'm going to put them in order smallest to largest, -1, 2, and 5. So with the synthetic division process, we're able to factor a higher degree polynomial equation and also find the zeros of that polynomial equation. To check our answers, we could take each one of those zeros, plug them into the original equation, and make sure they balance the equation. Awesome. So let's try the next example. The next example is just a tiny bit different. So let's see what this one has in store for us. First of all, how many solutions should we expect for this polynomial equation? Well, we have a degree 4 polynomial, so we should expect at at most 4 solutions. I keep saying at most because sometimes you have a repeated solution and it doesn't look like you have exactly 4 solutions, but we'll talk more about that when we study polynomial functions in the future. For now, we expect 4 solutions. To get started solving this polynomial equation, we want to identify our leading coefficient and our constant term. But do you notice there's no constant term in this equation? Well, all of our terms have a greatest common factor. So we're going to kind of combine what we've learned about solving by factoring and the rational zeros theorem all together on this one problem. Because there's no constant term, I'm first going to factor out the greatest common factor, which is x. So if we take that out, that leaves behind x cubed plus x squared minus 5x minus 2 equals 0. Now, if I set this factor equal to 0 and solve for x, well, we've got one of our solutions there. But we're looking for 4 solutions. The other 3 solutions are going to come from this polynomial equation. That does happen to have 4 terms, but it will not factor by grouping. So we're going to resort to our rational zeros theorem. So to do that, we need to identify our leading coefficient. That's going to be 1. And our constant term, which is now negative 2. And notice I'm just working in parentheses on that polynomial. So let's list our p's and q's. So the p's are going to include the factors of our constant term. That's going to be 1 and 2, both positive and negative 1, positive and negative 2. And look, we've got our easy case. The q's are just plus and minus 1. So every potential 0, p over q, is just the p's. 1 over 1, 2 over 1, both the positive and negative versions of those. So we've got 4 potential rational zeros, positive and negative 1, positive and negative 2. So let's just begin at the beginning. Let's take our first potential rational zero and confirm it with synthetic division. Now remember, I'm just working inside parentheses, so I'm going to pick up our coefficients 1, 1, negative 5, and negative 2. We'll bring down our first term and multiply and add all the way across the table. In this case, our remainder is negative 5. We're looking for a remainder of 0. So because our remainder is negative 5, we can rule out 1 as a solution. So we'll let that suspect go. All right, so that's not a winner. Let's look at negative 1. I'm going to use the same coefficients. Hopefully you're getting faster at synthetic division. Sometimes I get going so fast that I make mistakes. So stay focused. Okay, so it looks like negative 1 also is not a 0. Our remainder is 3. We're looking for a remainder of 0, so we can rule that out as a rational 0. Now keep in mind, several things can happen. None of those suspects in the list may be a 0. It's possible that this polynomial equation has all irrational solutions. But let's keep going. Next potential 0 would be 2. I'm going to come up here and use my space. We're interrogating this suspect with synthetic division. Are we going to find a winner here? Oh, it looks like we did. We found a winner. Because our remainder is 0, x equals 2 is one of our solutions. Okay, let's keep track of the algebra. So first we factored out the greatest common factor of x, and that left behind a degree 3 polynomial, which we're currently working on. One of the zeros of that degree 3 polynomial we just found is x equals 2. If x equals 2 is a 0, it came from the factor x minus 2. The other factor, remember, lies on this line. So don't forget, we started with degree 3. Okay, I'm looking at this degree right here, degree 3, working inside parentheses. And after one round of synthetic division, that represents a degree 2 polynomial. So let's assign descending powers of x, starting with x squared. We have 1x squared plus 3x plus 1 equals 0. So at this point, we know two of the zeros. We know x equals 0 and x equals 2. The other two zeros are going to come from this degree 2 polynomial. So at this point, we would attempt to factor that polynomial, that trinomial. However, there's no two factors of 1 with a sum of 3. So we're dealing with a prime trinomial here, or one that won't factor. But we can still outsmart that trinomial and extract the zeros, not by factoring, but by using the quadratic formula. So let's apply the quadratic formula just to this factor. So we're going to end up with x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. That's going to give us negative 3 plus or minus. Let's work under the radical. Under the radical, we have 9 minus 4, or 5, all divided by 2. So because of that plus minus there, we have two solutions, which means we have found all of our zeros. So let's go ahead and formally present our answer. I'm going to write all four zeros in a solution set, so I'm going to use my curly braces there. I'm going to start with the rational zeros. We had x equals 0 and x equals 2. Remember, x equals 0 is the first one we found. Don't forget about that one. And 2 we found from synthetic division. The other two are irrational. I'm going to go ahead and split them up. Negative 3 minus the square root of 5 over 2, and negative 3 plus the square root of 5 over 2. But remember, we were working with the degree 4 polynomial. We have found all four zeros. 2 are rational and 2 are irrational. So again, always attempt to factor your polynomial first. That's the easiest way to solve the equation. If that doesn't work, use the P's and Q's to figure out how to reduce your polynomial to where you can either factor it or apply the quadratic formula.